Okay, so just to revisit this problem on age at first word and Giselle score, and really just to recap the important numbers from the linear regression t-test. So we have a y-intercept of 109 point something, a slope of negative 1.1 point something, s is about 11, r is negative 0.64, r squared is 0.41, and we have a t-value negative 3.6 and a p-value of 0.001, degrees of freedom 19. Okay, so now showed you how to do that using a variety of different technologies. Now we're going to talk about how to do the entire thing using matrices. So you really only need 3 matrices to make this happen. You need an X matrix, which is referred to as a design matrix. And basically, it's a column of all ones and then a column of all of your X values. So in our case, this is going to be a 21 by 2 matrix. And then you need a 21 by 1 matrix, which is basically a vector of all of the Y values. And then you'll see here a little bit farther down this page, we're going to need a matrix of all, just a column of ones, a column of 21 ones. Okay, so the main matrix equation that makes all this happen is right here. X transpose X inverse X transpose Y. So X transpose X inverse X transpose Y. Now, the difficulty in notation with the calculator is that the calculator matrices only go up to matrix J. So what we're going to do is the X matrix in our calculator we're going to call matrix A. The Y matrix in the calculator we're going to call matrix B. And the coefficients, which would normally be B, the B sub 0 and the B sub 1, the coefficients we're going to put in a matrix called C. So, over to the calculator, second matrix, edit, matrix A. You need matrix A to be a 21 by 2 matrix, and the first column is just nothing but ones, and the second column is going to be all the values of X. So in this case, all the values of the ages. Okay, so then once you have that entered, then you need a matrix B, which is going to be 21 by 1, and it's going to have all of our Y values, which were the Giselle scores. Okay, so that all goes in matrix B. And then finally, you need a matrix J. So I'm going to go over here to edit and then scroll down to matrix J. And then matrix J is going to be 21 by 1, just like matrix B was. But the difference is matrix J is just going to be all ones. Okay, so time for the magic to happen. And just remember that when we found the A and the B, the very first way we found the A and the B, it was using these 3 equations here. One equation to find correlation, the next equation to find the slope from the correlation and the standard deviations, and then the next equation to find A. One of the beauties of doing this with matrices is we're going to get all of that out of just this one equation here. So X transpose X inverse X transpose Y. That's going to be parentheses, matrix A, transpose, second matrix math, item 2, A transpose A, close parentheses inverse, A transpose B. B is where the y values are. A transpose A inverse, A transpose B, instead of X transpose X inverse, X transpose Y. And the results of that we're going to store in matrix C. And this one equation, bam, there's our two coefficients, a y-intercept of 109 point something and an x-intercept of negative 1.12. And these numbers are exactly, with full decimal places, exactly the numbers we're going to get from any other printout. So if I go up and look at what we got from the linear regression t-test, 109.8738406. Exactly all those decimals, the exact same answer, and I'm just a little bit excited that this happens only using matrices. Then, next up, you want the residuals. Well, the residuals are the actual y values, which is matrix B, minus the predicted y values. And the predicted y values are found by doing our values of x, which are in matrix A, times our coefficients, which we just got done storing in matrix C. So I have this in the notes here somewhere. So B minus AC, and we're going to store that in matrix E, because the residuals are sometimes referred to as errors. So the B's are the actual Y's, and A times C is X times our coefficients, which is basically plugging each X into the regression equation and getting a predicted Y, and then subtracting that from the actual Y. These are our residuals. So we have the residuals in a matrix that's 21 by 1 also. And notice the very first residual is 2.03, which is exactly the residual we got up here when we put it into the equation, wherever that was. 2.03 for the very first residual. Okay. So we've got our residuals in matrix E. Now, to find S, S is the standard deviation of the residuals. So we can square the residuals by just multiplying the residual matrix times itself. So that's going to be E transpose E. Matrix E transpose and matrix E. So that will give us the sum of the squares of the residuals. The only problem with doing it like that is that the answer is actually given to us in a 1-by-1 matrix instead of just a number. So the way around that is to take the determinant of that. So let's do square root and then a fraction. Instead of just E transpose E, we're going to do the determinant. So second matrix math determinant of matrix E transpose E, close parentheses. So that'll just be the number 2308 as a number, because that's the determinant of that matrix. In the denominator, I'm just emphasizing that the degrees of freedom is n minus 2 on this problem, so I'm putting 21 minus 2. And then if we take the square root of that, that'll be s. So I'm going to store this in my variable alpha s. And that's exactly the 11.02 that we got from the calculator and from Excel and whatnot for our regression standard deviation S. Okay, so next up after S is to determine R and R squared. Actually, to determine R first. So I show here on the notes how to do it using the variance function, but I really want to stick with only doing matrices, and this is where the matrix J comes in. So this matrix equation here will give us R squared. And in terms of our calculator, that's going to look like this. So 1 minus a big hideous fraction. And in the numerator of that fraction is just the determinant of E transpose E. So second matrix math determinant of E, and then transpose E, and then in the denominator, this actually looks a lot like in the denominator one of our variance formulas where we had the sum of the x squareds minus the sum of the x's squared divided by n. We had a formula early on in the class that had that kind of format. The sum of the x squareds, but this is the sum of the y squareds minus the sum of the y's squared and divided by n. So determinant of B transpose B, second matrix math determinant of B transpose B, and then minus, and then another fraction. So I have a fraction within the denominator of the fraction. So this is going to be not B transpose B, but J transpose B. And in parentheses, the determinant of J transpose B, J transpose B. So that's the determinant, and then whatever that answer is, we are squaring. So that's essentially giving us the sum of the y's squared. And then to divide by n, we're going to do the determinant of J transpose J. J transpose J. And close parentheses on that. And I'm just going to double check over here. J transpose J, J transpose B. And this should give us R squared. And before I hit enter, just a reminder that our R squared was 40997. Okay, so 40997 is what we should be getting. There we go. So that calculation, purely involving matrices, gives us our value of R squared. Then, of course, we can take the square root of that and get our value of R. but we also have to take the negative of that answer because we had a negative slope. So there's our value of r. And then I'm not going to get too much into this next part, but you can also get the values of t from the matrices. So the A transpose A inverse matrix, when it's multiplied by S squared, so let's do that. S squared, so alpha S squared times the A transpose A inverse matrix. This is a matrix of variances and covariances for the coefficients. So the variance for our estimate of A is 2568, and the variance for our estimate of B is 0.096. So let's store this calculation in matrix F, so I don't have to keep re-entering all of that. I'm going to store that in matrix F. So now, if you take the square root of this entry right here, which is matrix F at location 2, 2, that square root is the standard deviation, or sometimes called the standard error, of our slope. And remember, our slope was negative 1.127. And so if I divide that by the standard error of the slope, which is 0.31017, that's the t that we saw on a couple of the different printouts of negative 3.63. So it's a little bit tough to get to that t, but the point is that you can get to the value of t that we saw on the regression output just by doing matrix manipulation also. And so the beauty of all of this is that we can get the exact same answers that linear regression gives us, or linear regression t-test. We can get it purely from matrices. That's not going to be on our final. It's not going to be on the homework on regression, but I just thought it might be interesting for some of you to see how that's all done using matrices to arrive at the same answers.